So my name is Michael Desrochers. I'm an undergraduate at SFU. I study chiral effective field theory and its applications to electron scattering observables. I do this work under supervision of Dr. Sonia Baca at Triumph in the theory group. And so first I'm going to provide some historical context to this work. In the 1930s and 1960s, there was an effort to understand the force between two nucleons. And the intention was to create an analogy to the electromagnetic force, where here you see two charged particles experiencing a force by the exchange of this virtual photon. These particles are electrons, in particular. Because the mass of the photon is zero, the range is infinite. So Yukawa won the Nobel Prize for figuring out that you can describe the nucleon-nucleon force in terms of an exchange of a virtual pion. And since the pion has a finite mass, or a non-zero mass, you get a limited range, and this is what was predicted by experiment. And then later on they expanded this model to include more mesons, and it was pretty good. It fit a lot of the scattering experiments at the time. Then in the 1970s, quantum chromodynamics was discovered. And it turns out the effective degrees of freedom were quarks and pions, or quarks and gluons rather, and not the nucleons. And so all the other models needed to be redone with these new degrees of freedom. The problem is that QCD is non-perturbative in the low energy regime, which is exactly where nuclear physics resides in. So we need to do something about that. In the 1990s, effective field theory was discovered by Steven Weinberg. And essentially what this does is it lets us create the most maximally generalized Lagrangian that has all the symmetries from QCD. And then what we do is we impose our own effective degrees of freedom on this Lagrangian. So in this case, we put the nucleons and the pions, and you can even add the delta particle later on, which is the excited state of the nucleons. And you can generate, but for our case, we just use the nucleons. And this allows us to write an effective Lagrangian, where this Lagrangian describes the interaction between two pions, this one, pion nucleon, and then you get various other permutations of pions and nucleons. In particular here, you'll be getting a nucleon-nucleon and then a nucleon-nucleon-nucleon interaction. So 3-body, 4-body potentials, just like that. And so one of the things we need to take note of here is that we need to keep the energies really low in this system, because if you have a very short wavelength, you're going to be able to see you're going to be able to see that the nucleons are actually made out of, they're bound states of quarks, right? And so the theory won't apply in that energy regime. So what we do is we keep the wavelengths large so that the nucleons appear as point particles, and we do this by keeping the momentum transfer lower than the chiral symmetry breaking scale, lambda sub b, and that's about 1 GeV for these systems. And then what we do is we take our Lagrangian and we expand that in terms of power of q over lambda. And this constant here, the c sub k, you can measure it in scattering experiments and get some estimates for that. And an interesting thing is there's a potential to actually calculate these things using lattice QCD. So that's a thing. I don't know much about that, but I do know that that is a possibility that's exciting. So what you do is you use your Feynman rules to generate Feynman diagrams for each term in this expansion, and then you'll get a leading order term where you have just a two-body force here. The solid lines represent nucleons, and the dotted lines represent the pions. And then you'll go to the next to leading order, and you still have two-body. In the next to leading order, you have three-body forces that begin to appear. And then next to leading order, you have more and more, right? And so that's kind of the description of this. Because q over lambda, if your momentum transfer is small enough, the increasing terms here will contribute less. Now, how do we test chiral effective field theory? Well, we choose to test it in electron scattering observables. So in electron scattering, you have an electron coming in, and then it exchanges a 4 momentum transfer with the nucleus. So it gives it some energy and some momentum. And this the cross-section for this process is defined as such. And what we're interested in here is this longitudinal response function right here. And it's defined as such. And so what we're doing is we're considering the longitudinal response function for Triton. And we notice that it's sensitive to the 3-body force, which is an interesting feature. So argon-18 and urbana-9, these are traditional high-performance nuclear potentials that are used in this experiment. And we notice that, this is the two-body, this is the three-body. We notice that with the inclusion of the three-body potential, we get a binding energy that is very close to experiment. But what we also notice is that with the inclusion of the three-body potential, we don't have a clearer resolution as to what's going on here. The data actually fits right in between. And so what we would like to do is we'd like to see how chiral effective field theory works in this scenario. And so this is the response function. Now what's interesting is that you have a final state wave function that's in the continuum here. And this is very difficult to calculate. I've heard that there's calculations for two-body systems. This is a many-body system, so it's very challenging to get. So instead, we don't do that. We take the response function and we map it into another space using this Lorentz integral transform. And this kernel has the property such that do some quantum mechanics and some algebra, really simple stuff, and you actually are able to get this, representation of the Lorentz integral transform. And this here turns out to be a bound state in the Lorentz space. And what it requires us to do is solve this Schrodinger-like wave equation with an inhomogeneous source term here. And this is something we can do with computer methods. And we do. And then what we do is we get this lit, and we invert it back to get the response function, and then we're able to get it. To further simplify, what we do is we take this charge operator, which is in the response function, and this is how it's defined, and we take this plane wave and we expand it using a multiple expansion. And so we'll get an isoscalar and isovector corresponding to these operators, and they will be expanded in this multiple expansion, monopole, dipole, quadrupole, etc. And with this, we're actually able to write the longitudinal response function as an expansion of monopoles. And we see that the monopole term contributes most to the longitudinal response function at momentum transfer 174 megaelectron volts over C. And so the quadrupole term here contributes very little, so we just go up to j equals 2 for this calculation. Now, we're going to test out our code, see if it works. So we confirm the published results from Leibman with his Urbana-18 Urbana-9 potential, and we see we agree. We calculate it, we agree exactly with his calculations. We know our code works now, unless both of our codes fail, then that's probably not likely. So what we do is now we try it out with the chiral effective field theory. In time for this talk, I've only been able to do up to the two-body terms, despite being next to the leading order. So this has the potential for four-body forces. I've only done the two-body terms in that table that I've shown so far, but more is to come. It's still illuminating to see what we get with this calculation. And it turns out this is a response function, the lid of a response function, and our calculation is in the right place. It's a little off, but this shows promise for chiral effective field theory. In addition, when we calculate the binding energies, we see that we're pretty close to the two-body calculation from argon-18. Yeah, so we're in the ballpark. We know we're in the right direction. Now what we need to do is the three-body terms. And so, as I mentioned, we have to include the three-body potentials in our calculation for these observables. And then what we also need to do is perfect the method for inverting the lits back to the original response functions. And it's relatively simple. It represents the response function in a function space, and then you just fit parameters and try to see if I'll explain that later. Anyways, the point is, if there's time. So in summary, chiral effective field theory is interesting and cool because it has a very strong connection to QCD. And so that's why we'd like to do this. We hope that by testing it on Triton, we can highlight the potency of this theory. And then later on, we'd like to test it on more complex nuclei and see if we can approach a general theory of the nuclear force. Thank you.
Thank you, Michael. Any questions?
So you were comparing this with the results from the Argon 18 potential calculations.
And they kind of added in the Urbana 9 potential as well, because that's the 3-body potential. Yeah.
Right. So what advantages are there to using the chiral effective over these other theoretical models?
Well, the Argon 18 and Urbana 9, what they do is they create a potential that'll fit experimental data really well, but it doesn't come from QCD. And if they wanted to, for example, discuss 4-body forces, they'd have to take out the Urbana 9 potential, add in, create a new 4-body potential, put it in. And chiral effective field theory, we hope, is going to have all the many body forces included in it. So it's a more unified approach, we think. They are more accurate because they have like double the amount of coefficients that they can nail down to experiment. But
Okay, cool.
yeah.
Any other questions?
So what does this response function actually represent physically?
It's an observable such that it's proportional to the cross section, obviously. I guess the best way to see it is it's a component of the cross section, and it's a function of the. It's observable in a strict quantum mechanical sense that like you can treat it as an observable, but I don't know if there's a physical, intuitive understanding of it.
Thank you very much, Michael.
No problem.
All right. Next up, we have Jason.